Hello and welcome back to another episode of Getting into Good Oxide. We've got pretty much exactly 50 minutes left or so we're a bit in a hurry. Also, one episode you entirely missed because of unforeseen issues of the non-technological kind. But on the bright side, we are now in a stage where we have implemented something that could be lookup prefix naively. We will be forced to go through that.
Copy paste the existing function, right?
No, we don't do that. We wrote it from scratch, and nobody can tell whether we really did that unless you tell the truth, which of course. Anyway, it's a copy paste thing, and maybe it's also the reason why it's not really working, because right now in theory it should already work for this test here, which is where is it? Can I jump there? If it fails, I can jump there. Now I get it. Because I think it makes sense. If it fails, there's some line number here, and that's why.
That does make sense.
It doesn't parse the code just yet. Okay. And what we do is we generate a prefix from an actual object that exists with a minimal length of 7. I always get this wrong. You have to say max 7 in order to get the minimal thing to be 7, which kind of makes sense if you think about it, but I always invert this. Anyway, computer science, really, it's not for everyone. This is why I need Rust. It kind of helps me anyway, so digressing, stop. So we create this prefix with the given length and stuff it into lookup prefix, and we expect that object to exist and to be non-ambiguous. Ambiguity checking we didn't implement yet, but we also expect this to always work right now. However, it doesn't, because this expectation here fails. Object isn't even found. And the object not found means we return none here, instead of a prefix lookup result, which could be ambiguous. The ambiguity case we don't even do yet. So in theory, this is clearly because we return a none here somewhere.
Yeah.
And the only place where we return a none is potentially, here we break out, here we return some okay. And here, if you don't have a candidate, we return none here. Question mark, quite a sneaky one. Alternatively, if the candidate doesn't match our prefix, or if matches candidate is incorrectly implemented, it wouldn't detect that. So this is also a reason why it might fail here. So do we not have a candidate, or is the matches candidate broken, or does it really not match the candidate, which means that something here is broken with the way we compare things with the binary search. All right, so what to do next?
Start from the top.
Okay. So what happens is we take the prefix, which is at least 4 hex characters long, or 2 bytes. We take the first byte, which is guaranteed to be there. This is all asserted by the prefix type. It wouldn't exist, this prefix, if there would be not fulfilling the invariance. And the first byte is then stuffed into this fan here. And the fan gives us the upper bound for the indices to look for. So that's an index here into our sorted or array that is sorted by object IDs. So what we do here is we have a sorted list of object IDs, sorted by in ascending order. And the sorting means that we can do a binary search. That's the great benefit of it. So we can quickly find things in that list. However, if you imagine we have 1 million objects, then if you start from the beginning always, then there's a lot of searches that we have to perform, a lot of comparisons. And this fan here allows us to obtain a range of candidates. So everything that starts with that byte, where is that located in my array? So only items that start with that, or only objects that start with that byte are searched.
So it's a counter of these first bytes, essentially, right? Because it always gives you the upper bound of a certain byte value.
It's you see how this works. There's a fan of how many possible byte values do we have? 256. It's like a directory. It says, okay, the last item in the fan at index 255, that's the highest value that a byte can have. That points to the total amount of objects. So that's naturally the total amount of objects, which is the size.
Oh, okay.
Yeah. So that's the upper bound. Of course, we can't go beyond that. And then we look at the previous index in our fan to get the upper bound of that byte, which is our lower bound.
Mm-hmm.
And this is how we get the range. And this allows us to greatly reduce, well, basically maybe cut, I don't know what that means to logarithmic complexity, but something by 256, and you divide it by, you greatly reduce.
Essentially, yeah.
Yeah. I mean, if the objects would be uniquely, distributed evenly, right? That's the word. And they should be, because SHA-1, SHA-256, they're great hashing functions, and this is what they do. They distribute evenly. And this really means, yeah, we have 1/256th of the size of array available to actually search. And
that's pretty good.
That sounds good indeed. And I never spoke it out. I never talked about this like this. I just always like, okay, you need a fan and you do it like this. But I never really visualized it, I guess. I just implemented it based on what was there. Roughly knowing how it works and probably having some sort of mental model, but I never spoke it out loud. Anyway, I guess because I can explain it, I understood it. But sometimes by explaining something, you're forced to truly, fully dig in like you never did before. Because it's not really necessary to do it in order to make it work, I guess. Yeah, but it's cool.
It works, yeah.
It works. Think about it like, what we are doing here, the value, you might think you're getting something, but I say I get even more, because I get to, get some more intrinsic understanding of what I'm supposed to know. And if not, I can look it up and know for the next time. And I guess that's, pushing me to the next level as well when it comes to learning. And ideally, you're getting something out of that too.
Oh man, 100%.
All right, upper and lower bound, and then we just do a binary search in that. It really is just the same thing, the same concept again. And yeah, binary search, get a midpoint, and then you get a candidate. And the real, how do you call it? The core of that binary search is really the comparison. And now,
I thought about if that's a problem if we're comparing like short prefixed nulled out version to a long hash, but I don't think that makes a difference, right? Because I'm guessing the comparison doesn't care about these null bytes in the end. They're just,
well, it does care. So I was, maybe you can visualize this. I don't know. So if you have a prefix here and then everything else is null. So let's just say we have a real short hash here with a prefix and that is null. And then we have XX, so similar prefix, right? We have an object that is 0, 1 and an object that is maybe 1, 1. Then the object and that is 2, 1. Okay. So this is our prefix, right? And right now, because we compare the whole object, it would literally say, I'm sorry, this object does not exist. Let's also add something else here. Let's add let's add something like this here. So we have a predecessor. And if we search now, it would say, I did not find that object that you're looking for, but here's where you would have to insert it. So we keep setting our candidate to that midpoint, and eventually we're out of options here. And then we go here. And then it would, what does it do? It matches the object ID at index, which is actually this one here. Like the index you get, or is it, which one is it? Do we get this one or this one? I always forget if you insert at the index that you get here. I think it's one past this one. You know, I think we should find this object here. I think we should.
Yeah.
Because that's the index we get, and at this point we have to literally insert this one to be properly sorted, so it should work that way. Because of the way this works, and no matter what you do, as long as we have one object here that has this prefix, it would sort it like this. So yeah, I'd say it should work, but might be wrong.
This looks right.
This means this is not
other
right.
thing in the the second equal case, or essentially the first equal case, it'll never really occur, right? Like I don't think we need it. Because it will never be equal unless it's full length anyway. So I think this if statement is kind of redundant here.
Yeah, it's something you wouldn't need. This would also work with this. It's more like, yeah, I agree. But also we don't run into this yet. Like our test will run into this. Why do I not get to jump back to my test? I don't get it. Okay, can I just run this and then it fails and then I can jump like this? Yes. So we will eventually get a prefix that is 40 in length because of the way this works here. Because the index goes up all the time and we have 900 objects here. So yeah, it's an optimization, I'd say. It might not be needed, but also it's not our problem right now. But it's something we can consider removing just to keep it less complex. And it's kind of, yeah, I would, because it would give us what we want, some okay. I don't think it's a problem right now, but let's mark it as something to look at. Okay, so then we have this, there's no candidate. And as long as we have any object we can find, we would have a candidate. And there should always be some object because, yeah, there's always a lower and upper bound, and we have 900 of these, and it would do the right thing there, I'm pretty sure. But to be sure, we can do this and just validate that we're not running into this. Because we also don't have tests for this one here, so maybe that just isn't working. So object is not found. By the way, it's kind of an issue here. You see, when these expects fail, they give you the message as a panic message. So now it's like, oh, object found, and it's not good. So this is why...
Well, I see, because when you write it, it's kind of different phrasing. You expect the object to be found, and then it's being turned around.
But I belong to the people who claim that I want to read it the way it makes sense when you read the code. And I say this is a rare case when it's actually hit. And then I'm okay with being puzzled a little. But also, there's the language team that makes the language better. And this is the kind of thing they can fix by saying, okay, we prefix this expect object to be found. Just prefix the expect here. And it's already better. And just something they can fix. So I say, I want a source code that does it in a way that is going to happen in future, I'm sure. And that reads well, which you do most of the time. So that's my explanation. Why I say, okay, little downside there, but
we keep it for now.
We keep it forever. And the language will change to suit us. Because that's how this works. But it really works that way. Their language team does an amazing job. I happen to know somebody on the language team, or who is the language team lead, and from what I can tell, they're very, very, ambitious about this, and they're listening. So, yeah, I guess what we can or should really look look at is this. Matches candidate. Does this work?
Maybe not.
And you know what? Since every prefix is technically valid, like every time we look for a prefix, it's a prefix that exists, right? So it's always gonna be true for our test. We have no prefix that we ever, like if this whole binary search thing works the way we think it does, we should get the right thing. It should be true. So if there is a bug here, this test here, I mean, this thing should now reveal it. Because now our test, hey, it does not allow me to go back to tests. Why is that? Okay, I don't know. Okay, anyway, let's run this and let's see how far we get with this. And in our tests, I think that's what I tried to say. We do have a test that assures that the entry ID we get actually points to the ID that we wanted to point to. And here you see that this is not the case. Let's jump there. Here. Okay, we found something. It's at this index. So now that we asked for this index, we compared with the actual source object ID that was used to create the prefix in the first place. And that should match, obviously, but it does not. This means that yeah, I mean, that's wrong for sure. The matches candidate is wrong for sure. Sorry, that's not wrong, probably. It's the binary search that is wrong. Okay, and we still have no test for this, but it's indirectly tested by our other tests, which could be enough. But for these plumbing crates, I do prefer to have some tests to back this up inside of the crate. So maybe we can do this first real quick. Just 2 little tiny tests that validate. We can see that something matches and also see that something doesn't match. So let's go there. There is valid inputs. We create a prefix. Yeah, so here we can already see that, right? Here we could already try, does it match our original object ID? Which it should. Assert prefix matches candidate or ID. Okay.
So you're not actually creating a test for it, you're just kind of stuffing it in the existing one to make sure that should be enough.
Yeah, I mean, there probably should be voices that say, shouldn't you have a proper test that says it matches this because of that, and it doesn't match that because, you know, like have some descriptiveness going on, and that's correct. But now I'm you know, just want it in there. And that's usually how I do it anyway. Like I start with stuffing it into something that has a lot of different test cases that are generated. And then once this seems to be, you know, whatever the outcome is, then afterwards I make 1 or 2 tests that are specific to this. For instance, prefix, yeah, actually, we have prefix from ID. Not matches candidate. TFN matches candidate, returns false if there is no match, something like that. And I guess we can just create one of these. This is new now. Hex to ID or the hex. Do I need that separately? We'll see. And yeah, how many? 7? Because why not? Let's also do something that is not so repetitive, maybe, just because maybe that's better to have more inputs. And then prefix shouldn't match. Prefix. Hey, where is? Oh yeah, completion in. No, where's my function? Matches candidate. Why does it not complete? I don't get it. Ah. Actually, initially, when IntelliJ started, the completion didn't work that well. The type inference didn't work that well. So usually you would not get candidates here, even though they're there and it should be there. But by now, it's usually a mistake if you don't see things.
The trust issues are still deep embedded, I see.
Yes. It's always easier to blame others, isn't it? It's deeply embedded into my mind, at least. It unfortunately is. It's a weakness I am at least aware of it sometimes. Okay, here we go. It all works. I do like IntelliJ. Mostly it works. Mostly I like it. Yeah, what kind of OID? Object ID. Null. It should not match null because definitely not there. That's the object ID I can imagine here. Git hash. Yeah. What about prefix kind? Oh, there's a brace missing. So this doesn't exist here. And I think it should just give you, oh no, maybe not. Maybe I can just do as OID kind. See, I think that's okay too. It gives me the kind of the hash, which in this case is always SHA-1. Because Git supports SHA-1 and SHA-256 in theory, at least, the latter one. And we already generalize or parameterize that so that we can make the transition more easily later. So that seems to work. Did it even run? Prefix matches candidate, returns false if there is no match. Can have another one. Hex to ID. So 1, 2, 3, 4, 5, 6, 7. Let's change this into an F. So now we are testing that the half byte comparison works, right? So if you would have done this in a test-driven way, if we would not care about this, like this is the literally supposed to, if we botch this, if you would only test for the, common case, this should now make the test fail. And it does. So that's a good test for exactly this specifically. And this is a test that validates that the common part, you know, I can even make this explicit here now that I started. So here we leave this the same and change something here. And that should test the common part. And yeah, doing this in test-driven way from the very beginning would have probably helped. I mean, it always helps me, and also to reason about it. But adding a test afterwards, I mean, it's okay too, I guess.
Verifying works.
Yes, but they should be there. And returns true if there is a match. It's very wordy here, but fine. So start with this, doesn't matter. Let's use 7 because it's the most complex case that we have. And then pull out the OID. And then this should match the candidate. because it actually matches. But what about another one? 1, 2, 3, 4, 5. What about this? This should be B, huh? And then something else. Like something that's obviously different. But that should also match. Right? Because it's only about the prefix here. Let's make it F. Maybe that's more obvious. Oh, and it should match, not be a mismatch. Okay, so matches candidate. I'm pretty confident that this is actually correctly implemented. All right, that's cool. One down. Then okay, there you go. And now back
I think we still have to return the OK value here, right?
No, because now, I mean, this was just an early exit. This was literally an optimization because the OK or the candidate is already saved here. Like the mid char is based on mid.
Oh, yeah.
We save it always. And then this might be the last one that happens, the last thing that happens. But in any case, we have a candidate. That's just what we want. Like get as close as possible. And then it might or might not be the right thing. We know that this doesn't fail, so we always have a candidate. But the candidate is wrong, probably because maybe the comparison doesn't work the way we think it works because of the nulls there that kind of participate. The weird thing is, we already concluded that it should work nonetheless with nulls or not. Because it's kind of the lowest possible value, right? Like having these nulls there, they do the right thing.
They should.
So, yeah, what's the candidate here? Let's just debug print something. Maybe that helps. Is it always null or 1 or something strange? That's obviously strange. Yeah, candidate is pretty much null. Okay. And then we break out. Okay, candidate, and what's the prefix then? Can also print that, should be printed in hex. Maybe the prefix is somehow strange. And the prefix is first 7 characters of something. And yeah, the candidate is not matching at all. And we can just for fun, we can just for fun print what's there in that range. Like, what's this? And maybe what's the next one? Maybe it's just a little bit off by 1-ish or something. Because we know it will fail right away, it's safe to just do this here and not do any bound checks. And it would panic otherwise because Rust does the bound checks no matter what. Oh. So look at this. The first one actually works, but now the second one, the second object, does not work anymore, because then it would be the next one that we should actually get. So, wait, am I reading this correctly? The prefix is the first object because we iterate through all objects. Okay. And the first object is indeed this one. So that matches. And the next one is this one. Okay. Now we come again We get a prefix of the object at entry 1. But our candidate is 0, which means it would want to insert this object here at 0, at the entry 0, because that's where it sorts into. And it should be easy to kind of understand why that is, I guess. God. This is why we'll never work at Google. That kind of stuff doesn't roll there. What? You don't know that right away? Huh? So, okay. So it should be easy. This one works because candidate is not null, but why does this? So, I mean, what's the number here? The number is this, right? So the second prefix is that number, and I would expect it to sort I mean, yes, it wants to insert it here. So null means inserted. No. It actually inserts it, would insert it at null. So if you say inserted here, it would go here and everything else is pushed further. So the candidate is wrong. I would expect it to tell me candidate 1 is the one. Yeah. And this would be the expected outcome of the binary search. Because this is how it sorts, right? It sorts right before this one.
Yeah. But the first one works. That's what's strange. Like,
yeah, coincidence.
There's some weird edge case or something like that when it's at the beginning or something. I don't know.
You know, I think the edge case is that this coincidentally works because it has a tendency to give us a candidate of 0.
Maybe.
What's the candidates then? What's the midpoints that we see here? Is there something strange about that? I mean, that comparison shouldn't care. That's definitely working. It's just a comparison. Yeah. So try 2. And you see it doesn't match. Try 1. And it's less. Yeah, because look. Because the prefixed object here, it sorts less than this.
It's always less, yeah.
And this is why it's less.
Yeah.
Even though, how should it sort? It should sort equal, because that's the first candidate. That's the actual candidate. And it will only sort equal if you do only the prefix comparison.
Okay. So we can't compare the whole string,
yes.
The whole hex. Yeah.
And that's the problem. So we should be able to, instead of comparing here, have something that makes a prefix comparison. Something like that. So matches candidate. What about comp candidate? Provided with a hashed ID, which is a full hash, determine if this prefix is determine how this prefix compares to it, only looking at the prefix bytes, ignoring everything else, everything behind that. So now we return an ordering, and can finally, you know, remember we kind of wrote that before. I wrote that intuitively because then you get to chain that. So compare that, and then just dump this here, then compare this. And the then only triggers if this is equal. If this is equal, then you have to look further. And if there is no extra byte, then you definitely can say this is equal. Otherwise, you compare these with each other. And that's that. And the good thing is now we do have tests that need to be adjusted. Is equal, matches candidate, comp candidate. Yeah. Now we really just compare for equality here. Yeah, we can even be better here. Not is equal. Now we compare this with something that is less. And now we compare this with something that is more. Oh, what is greater or equal is greater than, I think, huh?
I think so.
Ensure if ordering is greater, yes. It's greater is less, okay. Okay, no, this makes no sense anymore. Something like that, okay. And then lastly, this should be equal. This should be equal, nope. And down here, this is also just equal. So in theory, the tests, if it compiles at all, work. Now we have comp candidate, this should be equal. The beauty of, I don't know, is this functional programming maybe, but it's kind of beautiful. It composes so well. Okay, that is fine. We just created a function that we would need. And now it's about actually using it here. So the gist is here, the comparison. Comp. And we don't need the prefix OID either anymore. Prefix OID, the first byte, we use that a few times. Okay, fine. Prefix OID. Oh. Prefix comp candidate mid-SHA, and now we get a comparison based on only the prefix characters, and that should be a proper binary search. That should yield the expected result, unless, yeah, it should yield the expected result. Look, if it's equal, we now know that it's equal. I mean, here the prefix matches, and here is where we, we don't need that candidate thing anymore. Because if it's greater or less, we know it's not there. But if it matches, then it's the first potential candidate, and we know that.
Yeah, this is where we start checking for ambiguity later.
Yes, and now this whole part can go away. fortunately. And we know it's correct. We can really just return it. Return okay, sum okay, mid. And that's nicer. And ambiguity comes once we have a test. And then none otherwise. Oh, look at that. It's green. Cool. So in the remaining 10 minutes maybe. Let's see if we can get some ambiguity check going. Yeah, first of all, let's try to dial this down here. Is there some ambiguity later? Which you might not even detect yet, by the way. It might just be right by coincidence because it finds the right object, but it's still ambiguous. We don't know that. It should just always work now, by the way. Oh, cool.
Yeah.
That is interesting. Actually, that's unexpected because I really would expect it to always work. But look at this here. Ah, it did not work because it's just another object that we found. Like now we are in the territory of ambiguity. This is ambiguity right there. So we can actually keep this one and use it for ambiguity checking.
Perfect.
So 5 is good. And here we do this. So prefix new and 4, and that puts us right at the boundary where we would expect this to be. File, lookup prefix. Oh yeah, that's the problem. This is the problem. It's a bit unintuitive, but what can you do? It's not every input is correct.
Just what can happen.
Then the outcome is going to be an error. It's some error because we find the object, but it's ambiguous. And that does not look too good. We could potentially, you know, make a constant that represents this type so we can actually spell it out. Git hash prefix new. Yeah, we could. But for now, this should do it. Okay, this should show us ambiguity. And it should fail. It does fail. We actually get the wrong index. And the other one works now. Good. Failing test. And now let's make this test work by actually letting lookup prefix fail. Okay, cool. So
here we just look at the next one in line essentially, and then check if it's the same, if it has the same prefix.
Yeah. OID at index unfortunately has no failure mode. It expects to be inbound. So we have to do our own bound checking. If mid +1 is still smaller than num objects, then we can do it. Otherwise, we are at the end of this. Then it's the last object. And the last object is always, it's always unambiguous.
True. Yeah.
Like we just need another candidate to check. That's all. If you don't have that, then we know it's good. So if this one now, like if this not matches, then we are good. Should not be equal. That's all. So prefix comp candidate self OID at index mid +1. Let's call this next. Yeah, not as equal. Or if it is equal, then we know we return some error like this. Otherwise, return what we originally wanted to return. Some okay mid. Okay. And now Clippy would tell me, okay, look, you can definitely do this if it's smaller than that. And can you do this? Or is the logic then botched? Yes. No, I don't think you can do this.
That should work.
I don't know. That's Clippy. Clippy can tell us that it's working like this. Oh yeah, right. We have to return. So since each of these branches returns something, we can just declare the whole expression something that can be returned. And that should be it. And since that is kind of, it's not so nice to look at, make this the result and then return the result. Maybe that is nicer on the eyes. Is it nicer on the eyes? Look, now I just delayed the return, but still not working. Okay, whatever I'm talking about here, it doesn't matter because it's not actually working. Oh.
Could also just return the error and then get rid of the two else blocks and then just return okay by default essentially.
Yeah, that would be nice. So how do I do that?
So just return in the first the error essentially, like literally type return.
Literally type return here. No, wait.
Yeah, here. And then it breaks out if it is in this case, and then you can get rid of the other two else's and just return okay at the end.
Yeah. That's much better.
That should work.
Yeah, okay. That's much better. I think it should work too. Even though that's a nicer way of writing something that still does not work. Okay, we get 683 and we know that's not the right one, do we? Let's check 683. What's the object there? It should not be CFC33. It's CFC38. That's true. So which one do we want? Because we now look at the next one. We get this one, 683. We get this one, but our actual input is this one. So look, we have to look backwards, not forwards. Is this how it works? I thought they only look forward ever. Do we have to look around? Really? But in this case, you would have to, clearly.
Yeah, I mean now it's not automatically pushing it in front because we're only doing the prefix check, right? We're not including the null bytes.
Yeah.
I mean, so maybe you have to assume that can be a thing.
Yeah.
Or?
Apparently. But we have to, I mean, look, we tried to not check the prefix only. We did try that, but it didn't work. But also, think about it, the prefix now is like a partitioning mechanism, and we might just, because of the binary space partition, we might just coincidentally add at the last entry that has a particular prefix, like here. It just so happens to be at the end of that prefix range. And there can be more in front, and it would find them. Like, I think there can be one behind. There can be one behind. I mean, after that one, but there can also be one before. It's just like how it is, I guess. Because we don't know where we land in that range of indices that have that prefix. Maybe there's another one with that prefix. Let's see. Why not? No, we just have 2 with this prefix.
Okay, but it could be random essentially, right? Because you're always, the mid value is always half between the upper and lower bound, and then you could land somewhere in the middle of a prefix range, and then you'd have to check both sides.
I think so, yeah. And for this particular test case, like this already, we're quite lucky to have found this one, I guess. We can theoretically adjust the requirements to only need 1 byte, and then we have these 4 at least, maybe more. And then it might just work, because we happen to land here, and then the next one happens to have the right prefix, and then we know it's a ambiguous thing. Yeah, okay, well then let's look at both sides, I guess. Maybe that's how it's done. Okay, so if we can look forward, that's great. Let me do that. If we can look backward, if mid isn't 0 and the prefix candidate at mid -1 is the same, then return an error. Otherwise, we can happen to continue. So that should now find this one. Okay. Yeah, ambiguity works. Prefix still works. All right. So now we have to do 2 comparisons, and there seems to be no way around it. I don't know which one is better, to be honest. Like, should this be the first one because it's more likely to be ambiguous? Probably doesn't matter.
Yeah, probably just by coincidence.
Yeah, I don't really recall that this same thing happened in libgit2, but yeah, I think that's it for today's. I mean, that's perfect. What do I complain about? It works, and
it works.
That's what we wanted, and that can now be transferred to other packs as well. That's a multi-pack index, but the same thing should hold true for packs. So yeah, thanks a lot, Sydney, for helping me doing this. figuring this out.
Thank you.
And I hope we'll all have a nice weekend. Thanks everybody for watching. Bye-bye.
All right.